So we have India, Canada, Spain, and Israel being represented here. Love to see this diversity. So Kobi is a applied researcher and a developer of QEdit, zero knowledge blockchain that helps you build trustless coordination between people and parties. And he likes to, take action and build things rather than stay in the theoretical space. And Nicolas is joining us from, I believe like you were at cLabs for some time and helped us out as well. Is that correct?
Yeah, that's correct. So I'm currently working on Protocol Lab, but I help Kobi and Georgios build some threshold cryptographic library that is Celo using.
Nice. So we're
gonna talk about this.
Nicolas is at Protocol Labs, and he's the author of Drand, a distributed randomness beacon service, and they will be talking about this. I think one of the hardest things in cryptography is trying to get generate random numbers, and it'll be interesting to see how you guys are planning to solve that issue. So just for a logistics perspective, I'll let you guys, I'll let Kobi introduce the topic and take over the conversation. And if people have questions, feel free to ask in the chats. I'll probably ask questions all the way in the end, but if there are some basic questions that need to be answered, I might ask you guys. Otherwise, Kobi, take it over.
Cool, thanks Deepak. Thanks for the introductions. So actually what we're going to do is Nicolas is going to give the first part of the workshop, of the talk. And then I'm going to take over and describe how it's being used in Celo. So Nicolas, go ahead and feel free to introduce the topic and yourself.
All right, just need to, somebody share my slide, I guess. Okay. All right, so hi. We're going to talk about threshold cryptography, specifically its application to randomness beacon. For the first part of this talk, I'm going to talk about a specific technique which is used in Drand and the league of entropy, and then Kobi will later jump in and maybe explain some different techniques related, very close actually, related techniques that is being used in Celo. As mentioned before, I also work on the thing like Kobi, I believe we'll mention later with Kobi and Georgios. I participated to some Celo programming session, and so let's go into it. Next slide, please. Yes. So why do we need randomness? Okay. So we need randomness for many things. Let's start from the top level. In real life, we need randomness for actually a lot of things that we don't necessarily realize every day. For lotteries, jury selection, election events, all of these benefit from terrible randomness these days, and could benefit from much better randomness if we wanted to. We actually also need randomness in a lot of protocols, and especially into cryptographic protocols. So leader election in blockchain, I'm going to talk about this later on, more in details. For in Tor, when you need to choose your path, for example, in parameters for choosing your curves, or in schemes for DFM and exchange, and generally for zero knowledge proof. Even for clearance and divination. So we use randomness a lot, and actually it's a necessary component for many cryptographic protocols. Otherwise, we couldn't do many things that we are doing here. Next slide, please. So about the application of randomness in blockchain. In any blockchain, we need to run a leader election. So to know who is able to propose a block and who is able to create a block and which block are we going to accept in the chain. So the most well-known one is like a Bitcoin solution, which is proof of work, where nodes run a very computationally intensive task. And this is very reliable. It's been run for more than 10 years now. And lots of money thrown at this. Unfortunately, there are also some issues, like, for example, the economies of scale leads to centralization. And a couple of days or weeks ago, there was like a power outage in China that leads to 30% or something like this drop in the Bitcoin hash rate. So you can see electricity is playing a big factor here in centralization. We have also different techniques like on-chain randomness for proof of stake, where, for example, Cardano is used to run this. It's also a large financial network, much more recent than Bitcoin for. There are many variations of taking randomness from the chain directly. Most of them are biasable up to some points. Only Cardano so far, from one, Cardano has the most, let's say, proven protocol for taking this, but it includes high fidelity parameters, like a couple of days. One promising approach to derive randomness in blockchain is verified double delay function. Unfortunately, they're not production ready yet. It's been many years before that started. It will take a couple of years, I believe, before we see production ready hardware and software for it. So it's a promising approach, but still not quite ready to use yet. So next slide, please. So just a little quick slide on why do we need good randomness. So you could maybe perhaps imagine that randomness is easy to generate, but how would you do it? Well, actually, there's a lot of places where randomness has been generated in a bad way. So one famous example was the rig lotteries in the US, where an insider, someone who was in IT, actually was able to rig $14 million by using a biased random generator. He got caught at the end, but still, it's quite a lot. There was, as a funny story, I like to tell the ransomware as well. Ransomware author needs some randomness to encrypt the files they wish to encrypt and to ransom later on. And usually they take their randomness from the current timestamp. But this is very, very bad randomness, actually, because forensic analysts are easily able to detect this and try all the recent timestamp to find approximately when was it encrypted and quickly decrypt all the files. So it's also funny to realize that even the black hats need as well good randomness. Next slide, please. Next slide, please. What kind of randomness do we need? So now that we've convinced ourselves that we're using randomness a lot and that we need good randomness, what do we want actually? So we want randomness which is unpredictable. That's, of course, we can predict the next numbers at all times. There's no way. It's bias resistant. That means the distribution of random numbers should be uniform. It shouldn't be able to influence the distribution a little bit. So, but if you throw a dice, we shouldn't see more ones or twos than threes or fours. Publicly verifiable. It means anybody, any third party can verify the randomness has been generated correctly. Decentralized means we want a set of independent parties to collaborate together to generate this randomness. This is to allow a central point of failures, and we want also the randomness to be always available. Like this. Next slide, please. So how did the literature do before? So there's many papers on generating randomness. I'm just choosing different types of protocols that derive randomness. There is like an old one, like is a NIST randomness beacon, which is still alive today. It's based on quantum entanglement, so they take out the randomness from the physical law, and which is definitely unpredictable, as some of you might know, because when we measure the state of a quantum state, it's like we don't know where it's gonna fall out. It's just probabilities. And so this is definitely unpredictable. The problem is we still need to trust NIST to actually deliver it to us. Maybe someone is just writing random number on the PFL papers and returning it to me when I request them. We have no idea. We have to trust it. So it's not publicly verifiable. It's not decentralized as well. There was a next promising attempt is using Bitcoin, is using this chain itself. It was a promising approach. There was no formal proof of security from what I read, but the problem is also Bitcoin is quite centralized, still using proof of work and things like this. So we like to move away from this. There was a paper a couple of years ago called Randomness, which offered scalable and biased and unpredictable, publicly verifiable, decentralized randomness. So it was kind of a jackpot. It used solid cryptographic assumption, but the thing is it offers probabilistic guarantees, and it has a very large complex setup, large transcripts. So clients, it was when a client wanted to run this, it was a chain reaction that the client made a new protocol, and lots of nodes were need to communicate between together. It's a very difficult protocol to put in production, let's say, because there are different moving parts, and the transcript to verify around this is quite large, actually. It can be multiple kilobytes. So we wanted to see if we could do simpler and faster. So Randomness has been written in DEDIS, EPFL decentralized lab. And the system I'm talking about now is like the next generation after Randomness. Next slide, please. Yeah, so what we can do is actually use threshold cryptography. So threshold cryptography, the main idea is quite simple. So is you take a set of participants and you say for any operation that these participants can do, any subset of size T is required. So you can take any kind of set of participants, as long as it's there are more than T participants, then you will be able to do the operation. What kind of operation I'm talking about is like, for example, we can do signatures, we can do encryption, we can do many other things, actually. Threshold cryptography is kind of a magic tool, which we can actually decentralize a lot of protocols. But in this talk, we're going to focus on specifically how to derive the signatures and then the randomness from using threshold cryptography. Next slide, please. So how is this going to work? So in threshold cryptography, you usually have two phases. I'm going to talk about three, just specifically in this context, because we have the setup phase where the list of participants will run a setup. Okay, this complexity is O(n) squared, so it's like large setup, but you only need to run it once. Okay. Then you have the randomness generation phase. So periodically, a node will be able to run the protocol to quickly generate randomness, and which is publicly verifiable and has all the properties that we listed before. There's also a third phase that I added here, because once we have this group which is generating randomness, we may want to change group over time. Okay, so we need to change the group membership, and this is what I call resharing phase. Okay, we'll see how this works later. Next slide, please. So first, I need to recall some of the basics of cryptography. It's not complex, so if you try to follow, I'm going to go slowly on this, and if you follow here, you should get a good idea of how this all works. So I'm going to first introduce Shamir secret sharing. This is a technique invented a while ago, I think 40 years ago, by Shamir, and the goal is pretty simple. I have a secret, I need to share it. I want to split it so I can deliver some split it into shares, which I will give to some of my friends, for example. And if I want the secrets to be recovered, I will ask T of my friends, and I will be able to recover the secret. So here we have the secret S. So you cannot see my mouse here, so I can show. Yeah, so you have a secret S, which is in the polynomial on the left. You can see here, f of x equal S plus A1 times X plus et cetera, until the threshold. And then you will simply evaluate this polynomial at n points. So you have n friends you want to share your secrets to. So the first share, S1, will be the evaluation of this polynomial at F1. S2 will be the evaluation of this polynomial at the point 2, et cetera, et cetera. So S, remember, is the secret that we want to recover later on. So once all participants have their shares here, we can take any subset of these shares, any subset of size T of these shares, so T shares here at the left. Then we run them through what is called Lagrange interpolation. It's like, you think of it as a black box that you give T shares, it recreates the first polynomials here, f of x. So Once you have t-shares, you run Lagrange operation, and then you can recreate the polynomial, and then so you can derive the first coefficient, which is a secret S here. So you get S again. Next slide. So we've seen Shimmer secret sharing, where a dealer wanted to share a secret that he knew to n over participants. Okay. The problem here is that the dealer knows the secret. What we want is to have a protocol that generates shares for an unknown secrets. Okay, so nobody knows the secret, but everybody will have shares. That's the end goal, because once everybody have shares, they can put themselves together and do something with those shares instead of recreating the secret. I'm going to see later on how this works. So this is what we call distributed key generation. Okay, so at the end of this protocol, you will have n participants which each have a share, and a distributed public key which is publicly known, but nobody knows the secret key. Okay, that's the goal here. So how do we do this? It's actually pretty simple. We just run Shamir secret sharing n times. Okay, this is like the first major DKG here. So basically here we have, instead of having one polynomial, we have n polynomials, as we can see on the left. We have f1, f2, f3, fn. Of the first coefficient of each polynomial is the secret, so as S1, S2, Sn, etc. Okay, and then as before, as sigma secret sharing, all participants will evaluate their polynomial to n points to create the shares. So we have the first polynomial evaluated at the point 1, first polynomial evaluated at the point 2, etc., etc. Then second polynomial evaluated at point 1, second polynomial evaluated at point 2 in blue, etc., etc. And then, so as a participant, I will receive n shares, because each participant is creating a set of n shares for each participant. Okay, so I will have n shares, one share coming from each of our participants. And at the end of the protocol, I will simply add them up. Okay, so I will add all my shares for the, if I'm the first node, I will add all my S11, S21, SN1, etc. Then the second node will add S12, S22, SN2. I will add all the shares I receive. And this gives us shares of a secret key that nobody knows. Okay, nobody ever created this secret key. The secret key is actually the sum of all the secret coefficients that have been created at the beginning in the polynomial f of 1x, f of 2x, f of nx. But nobody made that summation. Nobody knows the final secret s. Everybody has only shares. Okay. So now that we have this, we can actually move on to the next step in threshold cryptography. But this is like really the basic, and if you understand this, then the rest is only application in this setting. So next slide, please. So I will not go into too much detail, but here we need to introduce some notation. So now that we have these distributed shares and this distributed public key, what can we do with this? One application is that we can do signatures with them. Okay. Regular signatures, like if you have on Bitcoin or whatever. Here it's a special type of signatures called BLS signatures, which is used more and more in recent blockchains, including Celo, if I'm not mistaken. For this type of BLS signature, we are using special curves, and we basically have some kind of a mapping here, but I will not go into too much detail here. But you can remember that BLS signatures is simply the hash of a message. So we can see at the middle here, hash of m to the power of s. S here is a secret key, okay? And this is my signature. So I just hash my message via, I don't know, a hash function SHA-256 or whatever. I put it to a point. I'm not going to too much detail, but I'm putting it to a point, and then I explicit it to my secret key. This is my signature. And then there is only one verification equation to check using this pairing E that I didn't define before, but I don't want to get too much into detail here. But this is very simply the verification equation of BLS signature, okay? Well, one thing we can easily do is, instead of using a secret key, a private key S here, we can use a secret share, a partial share, okay, what we derived before in the distributed key generation slide, okay. And this becomes, now we have partial signatures, because they are not created with a fully private key, they are created with a share. Okay, but the scheme is the same. We hash the message and we put it to the exponent si. Okay, so if we have the share I. Then with all these partial signatures, again, we run it through the Lagrange interpolation like before, or like in the secret sharing scheme, Shamir secret sharing scheme. And you think of it as a black box, and it will give us the final signature, which is a valid BLS signature, okay, under the distributed public key. So we can verify threshold BLS signatures as a normal BLS signature, even if it was made in a threshold way, even if it was generated by multiple parties. The verification is exactly the same as long as you get the public key. So that's nice. Next slide, please. So how does it work? Then it's quite simple, actually. When we want to generate randomness, we first broadcast the partial signatures to all of the nodes. On the message is known already. Okay, I'm going to talk a little bit more in detail about this later on. But all nodes know which message to send. They sign. They create a partial signatures and they broadcast it to all of the nodes. We simply need to gossip here. Actually, not even for broadcast. Gossiping should be fine. Then, as long as any node has gathered T partial signatures, then you will run it through Lagrange interpolation again to get the final signatures. And the randomness is simply the hash of these signatures, okay? We can prove that if you hash this signature, you get unbiasable randomness, and that gives all the properties we want. So we get, so this is like the big pictures of how do we use threshold BLS as a randomness source. Like we have this node that generate the setup, they have a private shares and a distributed key, and they periodically generate partial signatures. When we aggregate these partial signatures into regular BLS signature, we hash those signatures, and this is our randomness that we can use. And how do we verify it? Then, because we have the public key that has been generated during the distributed key generation, then I can verify if the final BLS signature is correct or not. I can verify that it actually has been created with at least T of these nodes, okay? And under our threat model, we assume that at least more than half of the nodes are honest. Next slide, please. So with this, I present you Drand. So Drand is a software run by a set of independent nodes that collectively produce randomness. So this is a software that exactly does what I've just presented just before, okay? We're using a threshold of n/2, more than n/2, and we're using the PLS12 381 pairing curves, such as Filecoin, E52, or Zcash. Drand is open source. It's coded in Go. It was started at the DEDIS in 2000. I started implementing it in 2015 or 16, and now is mainly supported by Protocol Labs. Drand has been since last summer. It's been tested, audited, and deployed. It's very simple to use. You can just make a curl command and you will get the latest randomness and everything you need to verify it. But more details on that later. Next slide, please. So how does it work very roughly? Now we've seen the cryptographic building blocks, how does the protocol works actually in practice. So Drand works by rounds, this notion of rounds. So round one corresponds to the first one, round two, the second one, etc. And so we have this time to run consistency where the first one is at time 0, the second one is 30 seconds later, the third one is 60 seconds later, etc., etc. We can change the frequency, of course, but right now the deployed network has 30 seconds. So what that means is we can always derive the run number for a specific timestamp. If I say if a lottery needs randomness in one day, they can commit to, okay, we'll use a random number at around 1001. It will be tomorrow afternoon. And so everybody knows which round the lottery is going to take from, the randomness from. So there's also this notion of chain in Drand that instead the message is actually the previous signature, previous randomness generated at the previous round and the new round number, okay? So each node knows which message to sign, and they actually run the protocol with this new message. Next slide, please. So one topic I didn't, I briefly introduced before is how do we change a group membership. So say we we have Drand. We have a Drand network launched by, I don't know, a set of 10 nodes, but then one of the nodes wants to leave, and we have 3 other nodes that want to join. How do we do it? Naively, we would need to run a new DKG protocol, new distributed key generation protocol, but that will mean that the clients, the one that uses Drand randomness, needs to change its public key. And it needs to follow the public key. And since we want this to happen relatively quite frequently, we don't want the end user to struggle with like following the keys. Keys updating is really a pain in traditional world, and it still is. So we want a mechanism that keeps the public key constant. Okay, so it becomes invisible from the client point of view, whether the group is composed of 10 or 17 or 23 members. Okay, it also allows to change the threshold and group size. So how does this work? This is just a small picture to show you that if we have, for example, a group of 5 nodes and we threshold of 3, we're in a resharing, we can change the group size. So here we have 7 nodes, we have a threshold of 5, and these shares are all new and the old shares are invalid anymore. Next slide, please. So how does this all work? It's actually very, very similar to DKG. But instead of putting a random secret in the polynomial, remember before each polynomial as the first component is a secret that each node chooses locally. Then as, for example, if I'm a node currently in the current group and I want to share to a new group, this group can be disjoint, by the way. It doesn't have to be common. Like an old group could pass to completely disjoint new group without any problem. So if I'm a current node and I want to share my share to a new group, then I will create a polynomial with S1 as being my current share now, okay? And with the rest of the polynomial being random. Okay, every current node does this. So we have S1, S2, SN for all the current members of the group. And they will, again, like in regular DKG, create their share. So we have the evaluation of first polynomial to the point 1, evaluation to the first polynomial to the point 2, etc., etc. The difference with the regular DKG, instead of adding the shares, so you can see to the right, I'm not adding them now, I'm running it through Lagrange interpolation. And this will give you the final share of for a new node, okay? This works because if you look at the left, the S1, S2, SN, etc., are all shares of the single secret of the DKG. And if you interpolate them, if you put them through Lagrange interpolation, they will give you the original secret that nobody knows. And this is exactly what we are doing here now. So this is why we don't add them, but we just put from Lagrange interpolation. There are some nifty detail with this, but I'm not going into too much detail, but that's a large idea here, high-level idea here. So now you've seen how we can reshare and how we move from one group to the other. And we can use this in Drand for refreshing the share for the same group. So even if the group membership doesn't change, we can still refresh the share. As in regular security advice, you should always not keep a private key for too long. And here you can do the same here. You can change the threshold, you can change the group size, and you can change the group memberships with this protocol. So this is really versatile. And this is actually using most of the same code base as DKG, actually. Next slide, please. So before going to talk about league of entropy, I just want to take one slide about the next step of Drand in terms of the software and the features it has. Right now, we have a broadcast protocol, which is very, it's a required assumption in DKG that any node can broadcast a message to all over nodes, and all over honest node will receive it at least. And this is much more complicated than it appears to implement correctly a reliable broadcast, a scalable one, and this is still a subject in research. So far, right now, we have this a little bit naive but working out fine protocol, which is O(n)² where everybody sends a message to everybody else. And we are looking towards extension where we can do something a little bit better, a bit robust, maybe recent result for TIMOS, which just came out, which is using parallel broadcast. So which would be nice. It would be more efficient and more secure than what we have now. Another feature which is very interesting to do is time lock encryption. So you can consider by just some changing one little thing, that basically by making the message to sign going from previous signature one number to only one number. So that means I can actually know which message the network is going to sign in the future. For example, in 2 days, I will know exactly which is going to be the one number. Then I can use this information to encrypt the message actually. And the decryption will only happen when the DRAM network will actually release randomness associated to this round. And in this way, you can rely on the DRAM threat model to do time lock encryption. Because only at the time where DRAM releases randomness, everybody will be able to decrypt your message. And this has a lot of application, including maybe preventing front running. And we have incoming projects that will try to work on it and see if we can integrate it to our platforms. Next slide, please. So now I want to talk to you about what are we doing with Drand. So this is where I introduce the League of Entropy. Maybe you've heard of it. The League of Entropy is a global Drand network composed of multiple independent and diversified organizations. It initially started in 2019 with 10 members, and we're now like more than 23 members. Celo is one member of the League of Entropy. We just added Zengo recently, but we have EPFL, we have universities like UPFL, UCL. We have ISPs such as PT-ISP and even Cloudflare. I guess it's considered an ISP. We have Illinois University as well. I mean, we have a large amount of group, and this is still growing. So what is the goal of the League of Entropy? Next slide, please. The goal of League of Entropy is to be a randomness as a service. So we are currently in our infrastructure, we have TNS that delivers naming information. We have NTP that delivers timing information. All of these services are really highly available. And we don't have the same for randomness. So we want Drand and League of Entropy to be a foundational internet protocol for randomness. So we want this to be, randomness as a service. Next slide, please. So what do we have now with the League of Entropy is we have a production-ready network, which is highly available and DDoS resistant. Each node is only talking to all over Drand nodes via IP firewalls, and we have proxies and front end. We deliver randomness via HTTP, via libp2p, so for gossiping, which is used in Ethereum, in Filecoin and over blockchain. We can deliver randomness via Tor, via Twitter, and anything you can think of. The code base is audited. There's a public report. We have continuous integration, etc., etc. We have health monitoring. So we have teams on the lookout for as soon as there's some alerts. There has been in the past, which all has been handled quite well so far. It is mainnet live from summer last year. So it was launched in early August last year. So far, so good. Next slide, please. And our governance model is, it's interesting because we are trying to, so far right now, Protocol Lab is the main support of Drand, but we don't want to Protocol Lab to detect the rules. So we have a kind of new guidelines of each time we want to change a protocol or we want to integrate new partners. So we introduce new partners on a quarterly basis. So for example, Zengo has just been added recently, and it has passed voting from the actual members to say if they want to accept Zengo or not. There's applications to register as a members. One very important criteria as well for the network is a diversity. So you can see here that we have like 42% in the US and 35% Sudan, for example, in terms of jurisdiction. In terms of infrastructure, we have 35% on AWS and 42% on premise. So that means that even if the whole AWS service is down for a while, it happened in the past, not all the region at once, but it happens in the past, then the service will still continue to run normally because we have more than the half of the nodes which are not running on AWS. And this is something we are trying to really keep an eye on and improve as a diversity and for jurisdiction, internet providers, and interest as well. So this is why we have universities, industries, organizations, non-financial organization, and things like this. Next slide, please. And just the last slide, I want to talk to you about who is using Drand right now. So the main production grade user of Drand is Filecoin now, which has launched last October. And so why Filecoin is using Drand is because for its leader election, like I showed at the beginning. So now each leader is actually using the Drand randomness to run the lottery to derive if they are eligible to produce a block or not, and according to their stake in the network, with their storage in the network for Filecoin. Here you can just see that just to show very roughly that the first command just fetch the header of a block in Filecoin, and just look for the beacon entries header, and you can see it's like start by 86, and then the second command curl https://drand.cloudflare.com just fetch the same random number but from the Drand network itself, and you can see the same, just to show you that Filecoin is really using Drand. There are other use cases of Drand being used in the wild. So we know for sure about kind of a gaming lottery application. We also heard about, but not using blockchain at all. And we also heard about being in contact with some developers, smart contract developer that are developing a lottery on the Cosmos blockchain and using Drand as a source of randomness. And it's like collaborative lottery. So we have been collaborating with them to deploy Drand verifier in WebAssembly that fits into a smart contract, an efficient smart contract. I mean, it's been very selective. So the ecosystem is growing, and yeah, we look forward to see what's happening in the future. Next slide, please. So that's it for me. If you want more information, you can go to http://drand.love and you will find everything in it. If you think your organization will be a good fit for being a League of Entropy member, then we'll be welcome to hear from you. You can find all the links and all the details how to contact us on the websites I've given. And here I will let Kobi talk about what the specific use case of threshold cryptography in Celo.
Okay, thank you, Nicolas, for the awesome introduction to threshold cryptography and distributed key generation, and Drand and Link of Entropy in general. And I'm happy that cLabs is part of the Link of Entropy. It's a really great ecosystem. Okay, so what I want to describe now is how threshold cryptography is used in Celo, both how it's used right now and how it's going to be used in the future. So what Nicolas went over is one use of threshold cryptography, which is to generate random numbers, like to create randomness beacons. But actually there are other different technologies and protocols that you can develop using threshold cryptography. For example, like threshold oblivious pseudo-random functions, and partially oblivious pseudo-random functions. And you can build a lot of interesting protocols that are useful using this. And specifically, the problem areas that we care about in Celo are the following. So we have phone number privacy. In Celo, as some of you may know, when you use the app, when you use the LoRa, you register with your phone number, and then you are able to send Celo to other people that are in the network using your phone number. But that poses a problem because that might introduce a privacy problem. And specifically, I'm going to talk about how we solve that. So if you only published, for example, on the blockchain, the hashes of phone numbers, that would be problematic because on the one hand, you want this mapping of hashes of phone numbers to be publicly available so that anyone can use the mapping to send Celo to other members. But on the other hand, you can't make the hash too computationally intensive because then it wouldn't be useful on mobile phones. So this is easy to brute force. So ideally, what you want to introduce is that you don't only hash a phone number which has a really low entropy. You also hash some kind of pepper, or it's a similar concept to salt, but it's something that is also secret. And if you do that, then you have higher entropy, and consequently, this is harder to brute force. But if you also do that using threshold cryptography such that many different servers collaborate in creating this pepper, then you're in the situation where you can enforce rate limiting policies. And what that allows you is to make sure that not only you increase the entropy of what you hash, you also make it such that nobody can request too many peppers for a specific phone number. And what that gives you is a better way to harden the hashes and thus protecting phone numbers. So specifically, the construction that we use in order to do that is some kind of very large, if you make it into an acronym, it's a verifiable threshold blind oblivious PRF. And basically it looks like this. So if you noticed in Nicolas' slides, the way you do BLS signatures is you take a message. So in our case, it would be a phone number. You hash it, and then you multiply it by a secret, this X, which is the private key. Now, what you can do additionally, you can make it such that if I want to get the pepper for my phone number, I can hide it from the server or the multiple servers that are going to see my request. So I can blind it. I can multiply it by a random factor B that nobody will be able to figure out what message I'm asking about. So this is going to be blind toward the server, and they will not be able to see what phone numbers I'm asking about. So this is kind of the process you go. You blind the message, the server assigns it with an X, and then you unblind it when you get it. And this is finally what you have, which is eventually turned into the pepper. So this is very, very, very shortly. And I really encourage you, if you want to see the overall end-to-end architecture of how it's used in Celo, and this is called the ODIS system, I strongly encourage you to watch Ross's talk. It's a Celo tech talk that is available in this link, which we will share later. And the implementation that Nicolas mentioned that we've collaborated on in the past to facilitate that is available here. It's a code base that contains distributed key generation and blind threshold BLS signatures. Right, so that's one use case where we use Celo. Another is randomness beacons, very similar to what Drand uses or Drand achieves. But in our case, we want to achieve on-chain randomness that is generated by validators. So one of the deficiencies in current randomness beacon protocol is that they have quadratic complexity. So whenever you want to set up new keys due to distributed key generation, it takes n squared, where n is the number of participants. And that becomes very heavy when you have many validators like Celo has, so more than 100. So what we worked on very recently is a new construction that is aggregatable. And this was joint work with Philip, Mary, Sarah, Gilad, and Amin. And this reduces the quadratic verification or quadratic complexity to quasi-linear if you use gossip, or linear if you get like some untrusted helper that's called an aggregator. And this paper is available here. And we're evaluating many different protocols, but that's one advancement in randomness beacons that we might want to be looking at. Another use that we have is, so I mentioned that if you want to send Celo to someone using their phone number, you can do it. But some users may want to have better privacy or stricter privacy. So we are also looking at protocols where I can only find you if you're looking for me. So that's kind of hidden matchmaking. And the difference is that security of your phone number or your privacy of the phone number does not depend on rate limiting like it has before. And this is based on left-right constraint PRFs, and also to improve security, we use it in a threshold context. And the last use case that I want to mention is password hardening and account recovery, where if I want to recover my account, let's say I lose it and I forget, then I want to be able to store it somewhere, but also store it securely. So maybe store it on Google Drive or Dropbox or something of that sort, but I don't want them to have access to it. So I want to be able to protect it with a passphrase or a PIN number, but these usually have low entropy. They're very short because you want to remember them. You don't want to write them down. So you can also use oblivious PRFs to enhance it. And we have a work in progress design based on partially oblivious PRFs, a threshold version of it that allows us to do this password hardening in order to increase the entropy of the PIN numbers of passphrases. So that's kind of a very, very quick overview of how we use threshold cryptography in Celo. And there are many other different exciting use cases that exist, but these are, I think, the few most exciting ones. And very quickly, I wanted to mention that this is unrelated to threshold cryptography, but this is something that we are deploying now. So we have Plumo, which is an ultralight client based on snarks that reduces initial synchronization for mobile phones significantly. And we just concluded a phase 1 of the snark setup recently. And we are gearing up to do phase 2. So these are some stats from phase 1. We have 55 contributions, and a lot of contributions outside of cLabs and the larger Celo and ZK decentralized communities. 10 rounds of contributions, and I encourage everyone that wants to participate in deploying this first of a kind snark to the world and sign up for phase 2 and participate. And that's about it. You can follow us, you can join Discord. We would love to have you there. And yeah, maybe very briefly, I wanted to mention that in contrast to what's been said in the beginning, I'm actually a cryptography engineer in cLabs for those few years. Thank you.
Thanks, Kobi and Nicolas. Let me see. I don't think people have any questions from the group. This was a good in-depth dive into threshold signatures and Drand. I really enjoyed the talk. And I do want to apologize, Kobi. Like, I know you stopped working at QEdit 3 years ago. There was some like miscommunication, and I just also been like doing way too much work in coordinating all these events. So yeah, like, so I do know Kobi. He's part of like cLabs, and he's the lead for the crypto team here at cLabs. With that said, any questions, Josh? You have any questions for Kobi and Nicolas?
so many questions. I think with everything in crypto, like the more I learn about any one thing, I realize everything's just a rabbit hole to learn a ton more. So yeah, I'm getting like my intro to crypto has been a massive crash course in computer science and information tech. So I got a whole bunch more things to start researching. So this has been super informative. It's a great, great overview of some more stuff to learn about. So thank you. It's super interesting.
Wonderful. Yeah. Again, I would like to thank Kobi and Nicolas, and we will take a few minutes break. So officially, I think the main stage has completed. We will be hosting. I'm hosting a Kuneco after party after in like, let's see what time we have here, 2 o'clock. So in another like 15-20 minutes, we'll be hosting a after party. Come join us. So you'll not be seeing more of these talks, but you'll get to interact with the rest of the community and everyone here. So I hope you can make it. Otherwise, we'll see you tomorrow. Any additional comments, Josh, to add?
Yeah, just that. This has been great. This is a wrap for the tech stage for day one, and it was great to just hear from so many community members and see all the different ways that like Celo's innovating in the tech domain, as well as like I hopped over to the main stage a little bit, and there's just so much to catch up on. So I'm gonna have to watch some recordings after this. But yeah, thanks for attending the tech stage, everyone.
Wonderful. Thanks, everyone.